The next topic that we have to discuss is about number theoretic algorithms. And before we start discussing about number theoretic algorithms, we need to recollect some basics from number theory. The agenda for this lecture is to recollect some basic elements from number theory which we need for discussing number theoretic algorithms. So, today we shall have an introduction about number theoretic algorithms, where basically we shall discuss about some basics from number theory. The set of integers is represented using this notation, and the set of natural numbers is represented using this. What is divisibility? An integer a is said to be divisible by another integer d when there exists a third integer k such that a can be written as d multiplied by k. If a is d multiplied by something, then a is divisible by d. For example, if you take a as 36 and d as 12, you can see that 36 is divisible by 12 because 36 can be written as 12 into 3. And because multiplication is commutative, d multiplied by k is same as k multiplied by d. So, here we can also say that a is divisible by k. Now, d is called a divisor of a if d divides a and d is greater than 0. So, divisors are all positive numbers dividing a number. This is a notation saying d divides a. For example, 12 divides 36. When d divides a is called a multiple of d. A is a multiple of d because a is nothing but d multiplied by k. If a is greater than 0 and d divides a, then it is easy to see that the absolute value of d, that is the positive value, is less than or equal to the absolute value of a. When I say absolute value, I mean the value without looking at the sign of the value. If negative 10, then the absolute value of negative 10 is 10. That is what I mean. So, when the value of a is greater than 0 and d is a divisor of a or d divides a, then the absolute value of d is less than or equal to absolute value of a, which is very easy to see. And if d divides a, we can say that minus d also divides a. For example, 12 divides 36, then minus 12 also divides 36. It is very easy to verify that from this definition. If d divides a, then minus d divides a because of minus k. You can verify that. Now, a lemma, which is a nice property about divisibility. If we have d divides a and d divides b, that is d is a divisor of both a and b, then we can prove that d divides ax plus by for all integers x and y, and this is what is called a linear combination of a and b. That is, if d divides both a and b, then d divides any linear combination of A and B. And Ax plus By for all integers x and y is called linear combination of A and B. That is A multiplied by an integer plus B multiplied by an integer is called a linear combination of A and B. So the lemma claims that if D is a divisor of both A and B, then D is a divisor of Ax plus By for all x and y. We can prove it. Suppose D divides A, then by the definition of divisibility, A can be written as D multiplied by a K1, where K1 is an integer. Similarly, if D divides B, then we can write B as D multiplied by an integer K2. So we are assuming that D is a divisor for both A and B. Now, what is Ax plus By? You substitute these values for A and B. You can write it as dk1 into x plus dk2 into y, which can be written as, if you take D as a common factor, k1x plus k2y, which can be written as D multiplied by an integer, because k1x plus k2y is an integer. So D multiplied by k3. So you are writing Ax plus By as D multiplied by k3. Then from divisibility we know that D is a divisor of Ax plus By, or Ax plus By is a multiple of D, and hence proved. So this is a very nice result. We prove that when D is a common divisor for both A and B, then D divides Ax plus By for all x and y, or D divides any linear combination of A and B. This is lemma 1. Please try to remember the result if you can. We can see example divisors. For 15, these are the divisors, you can easily verify. For 20, these are the divisors. Note that divisors are positive quantities dividing a number. And for any integer A, 1 and that integer absolute value, for example 1 and 15 here, 1 and 20 here, are divisors, and they are called trivial divisors. For any A, it is true. And all other divisors other than trivial divisors are called factors of a number. So factors are non-trivial divisors. Example, factors of 20 are all those divisors other than 1 and 20. Now, greatest common divisor. The definition is clear from the name itself. Let divisors A represent the set of divisors of a number A. Example, divisor 15 is this set. Then divisors 20 is this set. Then common divisors of two numbers A and B is the intersection of the divisors set. Example, for 15 and 20, divisors, common divisors is this intersection, which is 1 and 5. And the greatest common divisor of any two numbers A and B is the maximum from the intersection. For example, GCD of 15 and 20 is the maximum of the intersection, which is 1 and 5, the maximum is 5, which is the greatest common divisor. And now we can see some non-results about GCD. From the definition, it is very easy to verify that GCD of AB is equal to GCD of BA, because intersection is commutative. Now, GCD of AB is same as GCD of minus a comma b or GCD of a comma minus b, which is also easy to verify. And GCD of AB is also equal to GCD of absolute value of A comma absolute value of B. So if you want to find the GCD of minus 15 and 20, you can find GCD of 20 and 15, that is enough. And last result that we are recollecting in this slide is GCD of A comma 0 is absolute value of A, which also you can easily verify. Now we can have two more results. First is theorem 1, which is called the division theorem. Let A be an integer. A can be any integer, negative or positive, and n be a positive integer. Okay, we are looking at an arbitrary integer A and a positive integer n. Then the division theorem says there exist unique integers q and r such that A is nothing but q multiplied by n plus r. This is the division theorem. For any integer A and a positive integer n, you can write A as n multiplied with q plus r, where the value of r is between 0 and n. Example, consider an integer A 17, it could be negative, but we are in this example considering a positive number, and n as 4. So you can find a q and r. In this example, you can say that q is equal to 4 and r is equal to 1. You can easily verify that 17 is n, which is 4, into q, which is 4. 4 into 4, which is 16, plus r is equal to 1. And you can prove this theorem, but for the interest of time, I am not including the proof in this discussion. And here in the division theorem, you are coming up with a q and an r, where q is called the quotient of the division when you divide A with n. So q is nothing but the quotient of dividing A with n, and r is the remainder or residue of dividing A with n. So what is the remainder if you divide A with n, which is the remainder, which is written as A mod n, the remainder of dividing A with n, which is called the remainder or residue. Now theorem 2, which is a very important theorem. Let A and B be two integers with any one is non-zero. Either A is non-zero or B is non-zero. Then theorem 2 claims that the greatest common divisor of A and B when one of them is non-zero is the smallest positive element of the set Ax plus By, where x and y are integers. Not that Ax plus By is the linear combination of A and B. So it is the smallest element of that set. So we are claiming that GCD of any two numbers A and B when one of them is non-zero is the smallest positive linear combination of A and B, which is a very strong result. So we are claiming that the GCD of A and B when one of them is non-zero is the smallest positive linear combination of A and B, the smallest value of this form, Ax plus By. You substitute all possible values of integers as x and y and find Ax plus By. You will get an infinite set of numbers. then the smallest positive integer in that set must be the GCD is what the theorem claims. So, it is a wonderful result that we can prove it. Let S be a linear combination of A and B, Ax plus By, which is the smallest positive linear combination of A and B. You assume that S is the smallest value in this set. We are just giving a name S to the smallest value in this set. Now we are going to prove that S is the GCD. That is our aim. Okay, let S be the smallest positive linear combination of A and B. And let Q be the quotient of dividing A by S. Right? What is S? S is the smallest linear combination. Okay. And let Q be the quotient of dividing A with S. Then from the division theorem we know that the remainder of dividing A with S is nothing but A minus QS, because A is nothing but S multiplied by the quotient plus remainder. This is what the division theorem is telling us. So, we are actually looking at what is the quotient of dividing A with S. Okay, then this is true. Now, you substitute this value of S. Okay, S is Ax plus By. Then try to solve this equation, multiplying Q inside. And this can be written as, if you take A out, from the first two terms you are getting 1 minus Qx. A is taken as a common factor. Plus, here you take B as a B out, then you can say that it is nothing but B multiplied by minus Qy. This is in the form A multiplied by an integer K1, because 1 minus Qx is an integer, plus B multiplied by an integer K2. What is K2? K2 is minus Qi. Definitely minus Qi is an integer. So, this is of the form A multiplied by an integer plus B multiplied by an integer. So, it is a linear combination of A and B. So, we are saying that A mod S, or remainder of dividing A with S, is a linear combination of A and B. Now, we know that the remainder of dividing A by S must be between these two. This is what we know from the division theorem. Theorem 1 is saying that the remainder of dividing A with S is greater than or equal to 0 and less than S. Now, we have A mod S equal to 0. Why? Because A mod S is a linear combination of A and B, and we know that S is the smallest positive linear combination of A and B, and from this we know that it must be between 0 and S is the smallest positive linear combination of A and B by this equation, and therefore the remainder must be 0. So, we are proving that S divides A. Okay, we are proving that S divides A. Why? Because we got the remainder of dividing A with S as 0. Why is it 0? Because we saw that the remainder is a linear combination of A and B, and therefore from the division theorem, the remainder from the division theorem we know that the remainder must be greater than or equal to 0 and less than S. So, A mod S must be less than S and greater than or equal to 0, and also A mod S is a linear combination of A and B. So, what can be that linear combination? It must be greater than or equal to 0 and it must be less than S. but S is the smallest positive linear combination of A and B. So, less than S and greater than or equal to 0 means it must be 0, and that is what we are proving, and hence we are getting that the remainder of dividing A with S is 0, and hence S divides A is what we are getting. And similarly, if you take Q as the remainder of dividing B with S, we can prove that S divides B. Thus, we prove that S divides both A and B, that is the smallest linear combination of A and B divides both A and B, and hence it is a common divisor. So, S is a common divisor for both A and B. So, naturally we have the common divisor S, which is less than or equal to the greatest common divisor of A and B, because this is the largest among all the common divisors, and S is a common divisor. Now, GCD of AB divides S. Why? Because it follows from lemma 1. Since GCD of AB is a common divisor for both A and B. The lemma 1 says that if D is a common divisor for A and B, then D must be a divisor for any linear combination of A and B, right? And S is a linear combination of A and B. So, from lemma 1, it follows that GCD of AB divides S. I hope you remember lemma 1, otherwise please go back and see what result we proved as lemma 1. It says that, or it follows that GCD of AB divides S because S is a linear combination of A and B. Since we have this, that is GCD of AB dividing S, and S is greater than 0, we know that from GCD of AB is less than or equal to S. Why? Because GCD of AB is found to be dividing S. So, GCD of AB must be less than or equal to S. Now, we have these two results. S is less than or equal to GCD of AB, and GCD of AB is less than or equal to S. And these two, if and only if GCD of AB is equal to S. We have S less than or equal to GCD of AB and S greater than or equal to GCD of AB. So, S must be equal to GCD of AB. So, we are proving that GCD of AB is S, which is the smallest positive linear combination of A and B. With this, we are finishing this lecture. Today we have recollected some basics from number theory. We saw what is divisibility. We looked at the division theorem. Now we know what are divisors and what are factors. Then we looked at greatest common divisor. Then we saw that in lemma 1 we saw that if D is a common divisor for two integers A and B, then D must divide any linear combination of A and B. And at last we proved that GCD of two integers A and B is the smallest positive linear combination of A and B. And in the division theorem we saw that for any integer A and a positive integer n, A can be written as n multiplied by the quotient of dividing A with n plus the remainder of dividing A with n. Thank you.